Einstein takes only two facts of reality to set up special relativity. 1. The speed of light is the speed of causality. 2. Physics works everywhere, whether you think you are moving or not. These two facts, and our fact about the sun's light distance from Earth, helps us set up a great visual of what must be true. The sun is 8 light minutes away from Earth, meaning it takes 8 minutes for light to travel from the sun to Earth. Now imagine a situation where Earth has 2 suns, and it is set perfectly between the 2 suns. We know it is perfectly in between because it takes 8 minutes for light to reach the Earth from both suns. Now imagine that we send 2 rockets off of the planet, one on either side of the planet, complete opposite, aiming towards the 2 suns. Finally imagine that at some small time t, briefly after the rockets launch off, both suns vanish or explode or dim or brighten or the color changes, whatever, so long as it is a light effect which takes the Earth 8 minutes to notice. Are the events simultaneous to the rockets like they are for the Earth? Very apparently, they cannot be. For the rocket on the left side is closest to the left sun and sees that sun's change in less than 8 minutes, and sees the change in the far sun in more than 8 minutes, and vice versa for the rocket on the right. Therefore, what is simultaneous for the Earth was not simultaneous for the rockets, and therefore, if one's understanding of time is based on simultaneous events occurring with the hands of your clock, then time cannot be universal like Newton held. For time to be universal would require that all 3 observers, everyone on the 2 ships and everyone on Earth, sees both suns vanish or whatever at the same time, which would mean that light would have to reach the rockets, which are not in the center, at the same time, and at the same time that the Earth receives both simultaneously. This would mean that light would have to travel very fast for the far rocket, normal speeds for the Earth, and slower for the close rocket. This was the presumed position, which is ether drag, as the scientists thought it had to be the case that all 3 were experiencing universal time, and so the ether dragging effects of the rockets and the Earth must be speeding and slowing the light to make it appear as if universal time did not exist. After Michelson and Morley smashed the ether drag, the only conclusion left to draw was that what counts as simultaneous events to one person doesn't mean it's simultaneous for others. This brings us back to the solution to the Maxwell-Galileo problem. We said earlier, the only way to satisfy electrodynamics and the Galilean principle of relativity at the same time is if space and time are relative, as charge is invariant and does not change with respect to motion. We now know that velocity of objects must be relative to observers, as this means that different observers see the same events in space at different times. So we get 2 investigators, and they are placed in different frames of reference. One investigator is riding the wire. The other is riding the charged particle. Both investigators agree that 1. Someone is moving. 2. The particle and the wire move further apart after some time t. 3. Both agree that the speed of light is c. And 4. That physics is working. They are not exploding on-causally. Special relativity. The manner in which to apply these equations, known as the Loren Transformations, is similar to applying the Galilean transformations. In Galilean relativity, we saw that the speed of a thrown object was added or subtracted from the speed of the object it was thrown from, in order to have our math match reality and conform to each person's point of view. If a man on the shore wanted to know why the sailor thought the ball was only moving at 50 kilometers an hour, he had to remember that the sailor forgot about the relative motion of the ship. So the man on the shore subtracts the ship's motion and gets the same answer as the sailor. and vice versa. Loren's transformations make clear that the ether is basically a fixed quantum field and light travels through it at the same speed in all directions, and matter which interacts with that light also travels through it, but the light is only attached to the ether, so the motion of the matter does not change the speed of light. Because of this, you apply the Lorenz transformation by remembering that the sailor of the spaceship, which travels at the speed of 0.7 c, forgets about the relative motion of the ship. And so the man on the planet has to multiply the sailor's measurements of time and distance by a factor which keeps the speed of light constant. This provides us with the definitions of proper time and proper length. Proper time: the time that elapses in the frame in which events all occur at the same location. Proper length: the length of an object in the frame in which events all occur at the same time. Alice and Bob are our two investigators. Alice stands on a train platform, holding an extended rod affixed to a flashbulb in each hand, which she is extending a total of 2 meters apart, in an east-west direction. Alice, using her brain, fires a neuron signal which is to have both hands turn on the flashbulbs at the same time. The light which is emitted from the flashbulbs will reach Alice's eyes at the same time. As light must always travel at the same speed in the same medium, then the flashbulbs must be equally far apart from her eyes, and the lights, from Alice's perspective, can be said to be emitted simultaneously. Bob is on a moving train, adjacent to the platform. Bob is moving at 0.7 c eastward relative to Alice. If Alice is seeing both lights at the same time, then before Bob can see Alice at all, as the lights have not yet reached Bob, he uses his smarts and does the math. Since the speed of light is c always, since Alice has the two flashbulbs 2 meters apart, since Alice appears to be moving at negative v, then the light moving negative c must take longer to reach the left side of the platform than the light moving plus c reaches the right side of the platform. Therefore, if Bob believes Alice when she reports that she saw both lights, requires for Bob that the lights were turned on at different times. Bob would find Alice had to have turned on the east light first, then much later turned on the west light. Bob checks their math. According to Alice, the two light bulbs are 2 meters apart and they reach her at a time difference of 0. So Bob plugs this into the formula. The difference in time between the lights turning on for Bob is equal to gamma times the velocity of the train divided by the speed of light squared times 2 meters plus 0. Since Alice is moving, according to Bob, at negative 0.7 c, Bob finds a time difference of light flashes must have been 6 nanoseconds apart. Bob takes the flashbulbs and they repeat the experiment. Bob now sees the light reach him at the same time. So what will Alice find when she checks her math and diagram? When Alice has the lights, she reports that the lights reach her at the same time, 0 nanoseconds apart. And she did so because she pressed the buttons at the same time. Bob argues that Alice must be mistaken, that if the first statement is true, then Alice must have triggered the eastmost light 6 nanoseconds earlier than the westmost light, as light cannot violate causality. When Bob has the lights, he reports that the lights reach him at the same time, 0 nanoseconds apart. And they did so because he pressed the buttons at the same time. Alice argues that Bob must be mistaken, that if that first statement is true, then Bob must have triggered the westmost light 6 nanoseconds earlier than the eastmost light, as light cannot violate causality. Alice and Bob both agree that the other's far light had to have been switched on first. but both say that they turn their lights on at the same time. One possibility is that the far hand experiences time differently than the close hand. Perhaps this is a brain effect. Maybe our right hands attempt to balance out neural length differences with a default 6 nanosecond delay. Unfortunately, this cannot be true, as the delay again shows up if we switch directions, and then it is the left hand that appears to experience that time delay. Still, maybe it is a brain effect, where the hand furthest from the forwardness is delayed for some reason. So Alice and Bob construct a new experiment. No hand switches to remove this possible bias. Instead, Alice and Bob fix clocks to their east and west walls. According to each investigator, they see their own clocks as ticking at the same time, reading the same time at the same pace. However, the other experimenter must disagree that their clocks are synced. Despite not being able to see the other person's results, as the light takes too long to reach them, they know that the light that traveled in the direction of motion must have come from an earlier time, according to them, as the light from the back end takes longer to reach the investigator in the center. So both investigators know that their clocks appear to read the same time simultaneously, but they must also know that since one or both of them is in motion, then the light moving in the same direction as their motion must have been emitted earlier than it would appear. And therefore, if they approach the clock on the back end, they would see it speed up as they move towards its proper time. So the clock in the front is actually behind, and the clock in the back is actually ahead, such that the difference in distance the light needs to travel to reach the investigators balances out to appear to arrive at the same time. This is because light travels through the quantum photon field, or ether, as opposed to being a type of object that experiences time and space. Light is not contained in the ship like the air and man and ball and flies and fish were. This clock setup is merely another example of the relativity of simultaneity. The lights coming from the flash bulbs or clocks were emitted or reflected at different locations at different times. A weirder effect occurs when the two investigators, within their own frame of reference, record the same time, but based on the travel distance of a mover, the other must calculate that the other's clock is moving further. So if they are recording 1 second, and you know it traveled more than 1 second amount, their clock must be slow. One of the thought experiments that demonstrates this is called the light clock, which is a perfect mirror box that has a trapped photon inside, such that the photon of light bounces up and down in the box, and each time the photon does a number of bounces, it counts out the seconds of a normal clock. As a simple example, 1 second may be counted when the photon does one complete trip from the top to the bottom and back to the top. In reality, such a clock would require millions of bounces to count 1 second, as light moves at 3 × 10⁸ meters per second. So if the box were half a meter tall, then one complete trip would be 1 meter, and so to count 1 second would require 300 million complete trips, or 600 million minus 1 bounces. I have a different clock that we can use. It's our neurons. A lot of your nerve cells have a long cord called an axon, and that axon is insulated with what is called a myelin sheath. The axon is long, such that a single cell can reach far across the body to communicate its signal, and the myelin sheath helps to make that signal move faster. Together, the signal of touch can move at 80 to 120 meters per second. As most people are between 1 and 2 meters, a 100 meter per second signal can travel up and down the average person 50 to 100 times in 1 second. For a signal to be felt, it does not need to travel all the way to the brain. Some signals can be felt at the moment the signal reaches the spine, such as the knee-jerk reaction or reflex. So imagine Bob is 2 meters tall. His legs are equal in length to his torso and head, making his legs 1 meter long. As Bob moves along inside the train, which is moving at 0.7 c, Bob feels a pebble in his shoe. If we were to set up a neurology lab in the train and hook Bob up to an EEG machine to test his nerve impulses, we see that Bob's signal moves at 100 meters per second, or 0.1 meters per millisecond. So it takes 10 milliseconds for the signal to move from the foot to the spine. If we repeat this neurology lab in the stationary frame, Bob's nerves still receive the signal after 10 milliseconds. So we can say that Bob's nerves are constant. They always receive the signal in the same period of time, 10 milliseconds to travel 1 meter. But Alice is not convinced. Alice never got on the train and never saw the lab being done, but she trusts her colleagues would not make such a mistake. But clearly something is wrong. For when Bob was on the train, the signal that started in his foot traveled straight up his leg to his spine in 10 milliseconds. But his spine was no longer 1 meter away. After the first millisecond, the spine, Bob, and train had moved 210,000 meters eastward. If Alice calculates how long according to her clock it should have taken the signal to travel, given the motion of Bob and his train, Alice must argue that by her clock it would have had to take longer than 10 milliseconds. However, Bob counters and says that from his point of view, it was Alice who had the nerve signal that took longer than 10 milliseconds to be received. Given that he has the lab equipment using electrical signals that move at the speed of causality, he argues that it cannot be wrong that it took him 10 milliseconds, whether his frame is moving or not. And he argues that it was in fact Alice receiving nerve signals slowly, and therefore experiencing time slowly, and therefore seeing him slowly. If relative motion affected the speed of our nervous system, we would never move, as every time we started moving with a constant velocity that is different from the stationary Earth frame of reference, our nerves would fail to function properly and we would die, unable to signal the heart to beat and lungs to breathe. There is only one solution that solves the conflict. Velocity is relative, simultaneity is relative, and now we also know that time is relative. We already found the math that will help Alice find the time difference. According to Bob, his clock says 10 milliseconds, so she needs to write the equation delta t prime equals gamma times delta t. Delta t is Bob's time according to Bob, 10 milliseconds. And when Alice plugs that in, she finds that it actually took 14 milliseconds. Since Bob thinks he is stationary and therefore gets 10 milliseconds, Alice accounts for his motion, just like in Galilean relativity, and gets that Bob's clock is actually ticking slow relative to hers, not that his nerves are speeding up. Bob cannot witness this because Bob, his nervous system, his clocks, everything at that velocity is experiencing time differently from Alice. But according to Alice, Bob's clocks reach 10 milliseconds after what is really, in the Earth frame, 14 milliseconds. This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you.